Okay, today we'll talk about the Ramsey model in a second pass, and we'll basically look at the same ingredients of the Ramsey model, but we'll look at it in terms of a decentralized economy. Last time we looked at it from the perspective of Ramsey, which was a centrally planned economy, choosing the best allocation among all possible allocations available given the resource constraints. So we'll review that briefly, especially the techniques which are new to many of you, involving what we call the Pontryagin maximum principle, using, instead of a Lagrange function, we use something called a Hamiltonian function and characterize the first order necessary conditions for an optimum in this context, and then we'll apply that to the Ramsey problem again. And then we'll apply it to a decentralized economy with some remarks about why that's an important step. On the way, we will review and maybe deepen our understanding of the so-called phase diagram, which is a way of performing comparative statics and comparative dynamics exercises with the model. So changing certain key parameters and comparing how the model behaves under two different regimes, if you will, different parametric values for these key parameters. This is a very interesting device, not only to help us understand the model, but also to help us predict the outcomes following from changes in key aspects of the model. For example, impatience, or the depreciation rate, or something of that nature. And then I'll pause for a second and make some remarks about the difference between normative and positive economics. So this is a general point that might appeal to many students. This will basically be asking the question, when we discuss the way economics is organized, are we dealing with analyzing the behavior of people and economic agents, firms, governments, in the context of the environment that they're operating in, or are we making normative statements about what they should be doing with some goal in mind? And these two questions, of course, are very intertwined, and I'd like to discuss why we think it's useful to separate them. Then I'll talk about the decentralized model. I'll talk about an equilibrium in this model where the economy is populated by an infinite number of identical agents that have a problem that's similar to the planner's solution, to the planner's problem, but it's involving a private decision, meaning that the agents are trying to maximize their utility given a budget constraint, meaning they face prices and choose the quantities given those prices in a competitive environment. This would not be the case in the case of Ramsey, because Ramsey is a central planner. The social planner doesn't have to worry about prices because prices by construction don't exist. And comparing those two for potential parallels or even equivalence is one of the things economists have been doing for the past 60 or 70 years, trying to think hard about whether a decentralized market brings us close to what we would consider the best possible outcome, optimorum, and this equivalence is basically expressed in the form of the two welfare theorems of economics. And then I'll talk about some policy implications and finish up. Last time we motivated Ramsey's idea by thinking about a situation where a planner could conceivably choose many different allocations or policies or plans with the objective of making the residents or the inhabitants of this economy as best off as possible. Our natural reaction as economists is to assume that the market always does that, but it's always useful to think outside the box and ask, okay, well, if we were only constrained by the resources, in the sense of Samuelson, that prevent us from doing better, could we hope that the market achieves that optimum, or is it basically are there ways to improve on it? And Ramsey in the 1920s, late 1920s, thought about the intergenerational problem of trying to maximize welfare of successive generations of individuals, with an eye to the fact that capital investment, as had been sort of learned and discovered in the context of neoclassical economics at the time, was a way of transferring resources from the present to the future. Deferred consumption means consumption tomorrow, and the productivity of capital tomorrow means that that there's a trade-off between not consuming today and creating more consumption for individuals tomorrow. So writing this down in a rigorous way was what was Ramsey's contribution in his famous Economics Journal article in 1927. And this continuous time problem involves a lot of interesting mathematical ideas. And the way economists nowadays solve this, instead of the calculus of variations, which is what Ramsey did in the original, involves the maximum principle, so-called Pontryagin's maximum principle, and it requires the introduction of a new concept. Instead of the Lagrange function that we would be maximizing, we actually have an extended version of this called the Hamiltonian. And we had a cookbook list of first-order necessary conditions that need to be fulfilled to reach that optimum. And we, in the last hour, we actually looked at that carefully, and we characterized the idealized solution, again, without any recourse to markets or firms maximizing profits or individuals maximizing their own utility subject to a budget constraint. Rather, the Ramsey planner was doing this on behalf of the inhabitants of the economy. This analysis gave rise to some elements that are useful for us. One is called the phase diagram, which is a diagram of different variables in the model. In a two-dimensional model, we'll consider there'll be two variables, and both have characterizations of dynamics when the state of the system is not located on one of the or two of these isoclines that we isolated, which are isoclines when the rate of change, the absolute rate of change, is equal to 0. And when those cross, the intersection of those curves would represent the potential steady state that we could look at. And rather than doing a lot of mathematics, I sort of appealed to some general results that the crossing point would be stable under the conditions we've studied, but it would actually be saddle stable in the sense that there's exactly one path that leads to the steady state. Every other path that begins off this saddle path would eventually lead to results, either infinite consumption or zero consumption, or basically unsustainable paths. So with an eye to the steady state, we will restrict our attention to these saddle-stable solutions to the Ramsey problem. Just to review the notation, consumption per capita was denoted by little ct at time t. T is the time index, starting at 0 and going to infinity. The utility function is general at this point. We'll keep it general for this lecture. It's basically got a positive first derivative and a negative second derivative. Call it a concave felicity function or instantaneous utility function. Little k is the capital stock per capita at time t, and since technology isn't changing, we won't be using effective labor units or units of effective labor. We'll normalize by the population. So little k is basically capital K divided by capital L. And capital L is growing at rate n, and productivity isn't growing, so little a is equal to 0. Y is produced output per capita, and it's produced using an intensive form production function, which has its origins in neoclassical theory with constant returns to scale, meaning the first derivative is positive and the second derivative is negative. We're dealing with a concave production function. Delta is the depreciation rate on physical capital. And then we have this issue of what the impatience of the individual agents is, and we'll use the instantaneous discount rate, theta, to denote the private and the central planners' discount rates. applied to individuals. So individuals that are growing this would be the rate at which individuals' utility in the future is valued relative to the decision maker at t equals 0. So one way of thinking about this is that people have altruism over future generations, even though they're unborn, but they're treated as if they're the children or the offspring of the private decision maker or the central planner. Okay, so that's just a review of the notation. The model itself stipulates a utility function that's an integral, so it's a sum of, if you like, of instantaneous utilities in each period of time going from 0 to infinity, where the utility at period t is deriving solely from consumption per capita. So think of theta now as a discount factor that applies to the individuals whose numbers are growing at some rate n. And this is discounted, so the discount factor is continuous, so we have Euler's constant raised to minus theta t. Capital accumulation in the intensive form would be summarized by the next equation, which says that the first derivative of the capital stock per capita with respect to time is effectively a race between the numerator and the denominator. The numerator grows at rate capital K dot, holding LT constant, and the denominator is growing at a rate related to the population growth rate, which is in this economy is fully employed, and therefore it would grow at rate little n times little k. It's a standard expression. And we can write, having inserted the investment policy or the investment consequence of consumption would be y minus c in every period t, then this can be written as the form of f of kt minus ct minus n plus delta times kt. So this is the classic sort of intensive form accumulation equation for the economy's capital stock, irrespective of whether the central planner is choosing the policy or the individual agents. So this is like the ironclad rule of motion for capital, which cannot be evaded by clever planning. It's basically what the planner and the private agent have to deal with. It's just the physical laws of resource accumulation. There's an initial condition that both the agent and the social planner would have to take care of. Now remember, in the social planner's perspective, there are no markets, so we don't have to worry about that aspect. But what is important is whether the central planner is able to allocate the consumption that she wants to all the generations she wants to, and still obey the transition equation for the capital stock. So if the central planner wants to give a lot of resources to the young generations today, or to the people that are born in the next few periods, that will have a cost of having less capital for the future generations that follow. Okay, so now we have the three conditions for optimality from the maximum principle. Pretty straightforward. As last time in the previous lecture, in the fifth lecture, we have the first task is to set up the Hamiltonian function. Then we have to consider the first derivative of that Hamiltonian with respect to the control variable. And in this social planner's problem, there is only consumption per capita. Okay, that's the control variable. All else results. The change, the temporal evolution of the capital stock results from choosing CT given the capital stock in period t. So that derivative has to be set equal to 0. That's like a first order condition that you would expect from a Lagrange type of analysis. Therefore, it should be easy to follow. The second condition involves the derivative of the Hamiltonian with respect to the state variable. And in this particular setup, we have one state variable, which is the capital stock per capita. And the rule of thumb says to set the derivative of the state variable of the Hamiltonian with respect to the state variable equal to the negative of the derivative of the co-state variable with respect to time. So this is an optimality condition which guarantees that the rate of change of the shadow value of the state, here we would call this the marginal utility of consumption, also obeys a certain intertemporal law and can't be arbitrarily chosen if the agent wants to maximize, or if the planner wants to maximize utility. So this is the co-state variable in this problem. You can think of it, in this problem, it's going to be either the Lagrange multiplier multiplying the budget constraint, the periodic budget constraint in each period t. It will also be identical to the marginal utility of consumption. So in a sense, consumption could also be considered a transform, a monotonic transform of this co-state variable, the shadow value of capital stock. And this is going to have a dynamic that's determined by this negative derivative with respect to time. So it's the rate of change of that derivative, the rate of change of that co-state variable with respect to time will kind of govern the way the value of this maximized problem will behave over time. The last period, the last condition, restricts our attention of all the paths that might fulfill conditions 1 and 2. It restricts our attention to those in which the agent, or the planner in this case, does not choose to keep on deferring consumption and accumulating a large capital stock that is so implausibly large that it would make sense for the social planner actually to reduce that value of the capital stock in some distant period, and in doing so, the social planner would be able to increase utility for all generations between then and now, or increase utility for the generations for which the capital stock would be consumed. So this is a way of guaranteeing that the social planner doesn't obey 1 and 2 and forget about the fact that all this capital might be accumulating over time, which should be used for production, but actually is only used to produce goods that are never even consumed. They're just producing more capital goods, more production goods in the future, and this would not be characteristic of an optimal plan. So it's really choosing a path out of many potential paths that meet the first and second first-order necessary conditions. Okay, when applied to the problem we've just looked at a few slides ago, this would basically mean taking the Hamiltonian that we derived last week and differentiating with respect to CT in every period t from 0 to infinity, and making sure that that's equal to 0. Okay, so there should be no gain from very small variation in consumption path in terms of expected utility or discounted utility today, and that would characterize optimality. So that first order condition can be rewritten concretely as the first derivative of the utility function with respect to consumption today is equal to lambda t, which is the co-state variable attached to the resource constraint of the social planner. So if you think about that, that just means that basically the marginal utility of resources at any point in time should be equal to the value of getting a little bit more of those resources in the resource constraint, and that must be also equal to the the marginal utility of having an extra unit of capital. So you can think of that as the very standard first order condition. And in the form it takes, you can see that we can immediately eliminate lambda t from the problem. We'll do that later on. The second first order necessary condition involves the present value of the co-state variable, which is not the same thing as the current value, and we discussed that last week. So the functional that we would be concerned with would actually have this discounted value of lambda in period t, where the discount factor is e raised to the minus theta t. Okay, so that's a convenient way of dealing with this problem, because when we look at the behavior of the social planner and the planned economy, we want to look at lambda t, which is the current value of relaxation in period t, of relaxing the resource constraint, and not the present value from some perspective of an arbitrary t equals 0, at which the time the planning was actually executed. Okay, so this first order condition can be seen in the following. And if we substitute the definition of mu, which is the present value, if we substitute the discount factor times the current value, then we have lambda t e to the minus theta t. And if you differentiate that with respect to time, you get the last term. So you can see the advantage of doing it this way is that we can effectively make the e raised to the minus theta t disappear, because it's going to cancel from all three terms. And then we get the fourth line of this slide, which says that the marginal product with respect to capital in period t is going to be related to the population growth rate, the depreciation rate, the impatience of the central planner, and a term related to the capital gain involved from the perspective of the capital, from the central planner, the capital gain meaning the change in the valuation of having capital in period t. It's like an adjustment, if you think about it, because indeed when you're, if lambda is changing, then the shadow valuation of the capital stock will be changing over time, and the central planner will, if you look carefully at this, you can see that it's basically going to be the capital stock will have a marginal product that's related to the population growth rate, the depreciation rate, the impatience rate, and also with a correction for the appreciation of the value to the central planner in period t. So this thing will be rising if consumption is low and is increasing over time. So this is an important aspect we'll look at later. And on top of that, we have this, if you like, this cake-eating condition, which guarantees that the capital stock does not have a valuation, again, which would be this part. As we go to infinity, that would make it possible for the planner to actually increase utility for the population by reducing the capital stock, by literally eating the capital stock at any point in time, and at very, very distant horizons. So to rule that out, we let t to go to infinity and just set that product equal to 0. And that kind of rules out that case. We won't use this condition directly in the analysis, but it's important to know that these types of paths where the sort of a exaggerated accumulation of capital stock is taking place will be ruled out. Okay, so again, the trick we already discussed, eliminating the term mu, which is the present value or the present valued multiplier, and substituting for this discounted version of the current multiplier allows us to simplify that equation significantly. Okay, so we can do that, and we get the following three equations. And the first two are the ones that are going to concern us most. This one and this one. This is, again, still review of what we did last time. I haven't gotten to the private private household's decision yet. So this model has the really attractive feature that you can eliminate lambda completely from the analysis. So lambda and consumption per capita move monotonically in opposite directions. There's monotonic functions of each other by assumption. So as the economy increases its per capita consumption, the marginal utility of consumption will decline. And if you substitute lambda in the second first order condition, characterizing this optimal consumption path, optimal capital per capita path, we can rewrite this equation as simply one that involves capital per capita and consumption per capita. So this is our first step in making the phase diagram possible to work with. Okay, so we'll focus on that one. And we can also observe that we can basically write consumption on the left-hand side, and as a function, the rate of change of consumption is a function of, and it could be a variable multiplier times the difference between the marginal product of capital and this long-run level to which we will approach, which is the sum of the growth rate of the population, the depreciation rate, and the planner's discount rate. And this right-hand term can be manipulated. Dividing both sides by strictly positive consumption would give the rate of consumption growth on the left-hand side per capita as a function of the same arguments I discussed earlier, multiplied by something that's related to the elasticity of intertemporal substitution. Okay, so this term, which is kind of the relationship between the derivatives, the first and second derivatives of consumption scaled by consumption itself, it doesn't need to be a constant. It could be a constant, and there are some functions that have this constancy, but in general, we call this the intertemporal substitution, elasticity of substitution for this utility function, U, and this gives us kind of it's the reaction of the slope of the utility function as a function of the concavity of the utility function, or you can think of it as the rate of change of the concavity of the function as a function of its slope. Okay, so in a sense, it's kind of, in this class of utility functions, it's alternatively a measure of readiness to push consumption into the future when given the incentive to do so. So the reaction in terms of percentage change of the ratio of consumption tomorrow to consumption today in response to a 1% change of the intertemporal price of doing so. Okay, it's also, the inverse of that is the measure of relative risk aversion. Since there's no risk in this model, there's no room for interpretation of that aspect. But in a model with uncertainty, it would actually be a part of the story. But here, it's just a measure of how quickly, how readily consumers are ready to change their consumption plans in response to a change in the incentive to do so. And the incentive to do so can be thought of as this term here. This term gives us, because it may be changing over time, it gives it's a summary of the incentive to postpone consumption over the future. So the marginal product of capital exceeds the rate of growth of population, the depreciation rate, and impatience, then you would get a larger reaction to a change if the elasticity of substitution, intertemporal substitution, is higher. The second equation is simply the equation of motion for the capital stock, the Goldsmith equation in per capita terms. We already learned that from the Solo model, so there's nothing new to discuss at this point. Okay. This is just writing down what I said in words. Now, the Keynes-Ramsey rule is just an implication of those first-order conditions. Optimally chosen consumption will increase. It will remain constant or decrease depending on whether the right-hand side is positive, negative, or constant. or whether the marginal product of capital net of population growth and depreciation exceeds or is equal to or less than the rate of time preference. Okay, this is called the Keynes-Ramsey rule, and it's basically a rule of optimality that governs the intertemporal path of consumption. So if the marginal product of capital is high and you're optimizing your consumption path, then it must be the case that consumption is rising over the near periods, because the high marginal product of capital is the incentive for people to defer consumption, not to consume. Doing so, putting the resources into capital to produce more, and that gets paid off in some sense in a higher per capita output in the future. Okay, so this Keynes-Ramsey rule is the basis for many economic analyses, and it's kind of it basically says nothing about the level of consumption. It really tells us about the intertemporal path of consumption. So it's consumption today relative to consumption tomorrow. To get the path, we need to know the total level of resources available to the agent. We need to, in some sense, insert this into the budget constraint and solve for the level of capital stock in period 0 that would be consistent with this path that we've isolated. So now the next point is actually, in this class, we won't do any sort of solution of these models. We won't even use the computer to solve these models, although we could do that. The solutions tend to be very sensitive to the assumptions you make on the functions, and therefore it may not be that much value. There may not be much value in doing that compared with just having an intuitive understanding of what the model predicts under many different specifications. So that's why we use the phase diagram in this class. The steady state would be, going back to the equations of motion, would be, steady state would involve both of these terms equal 0. So when capital per capita stops changing, and when consumption as a rate of growth stops being positive or negative, is going to be associated with a steady state. So we can set those equal to 0, and we can plot those objects. Okay, so the first one is simply it looks a little bit like our Solow model. The equilibrium in the Solow model for output, we discussed that in the very beginning of the course. Says the marginal product of capital per capita is equal to a sum of impatience, depreciation, and the rate of population growth, just like the golden rule did, except now we have this impatience term added. So remember, Ramsey planner is trying to optimize utility from the perspective of some initial condition. In the long run, it must be the case that consumption per capita is being maximized. So that's kind of what our intuition would say. But in the Ramsey story, we have a positive discount rate. So theta is positive strictly. Could be, we could discuss other worlds where it's not, but this impatience gives rise to all the discussion that Ramsey had in his work on whether it's just for the planner to favor generations that are near in temporal terms to him or her, as opposed to generations that are far away. But independently of that discussion, you can see that this is different from the Phelps golden rule discussion, because Phelps didn't have a discount factor. He was just maximizing consumption per capita, and that would be like setting Ramsey's impatience equal to 0 in a world where there's no technical progress. So these are conditions that are familiar to us. And you can think of this from the planner's perspective as relating the marginal product of capital on the left-hand side to the social opportunity costs, meaning that these resources could be allocated to consumption, but they would have to be, in a sense, will have to cover their way. They're going to have to guarantee that there's enough output to cover the constantly growing population, as well as the fact that capital has to be replenished after depreciation, and that the social planner might also be impatient. Okay, so these isoclines that I discussed are like combinations of KT and CT that have a constant slope or rate of change with respect to time. Okay, and we're only considering the isoclines for which this rate of change is equal to 0. Okay, so it's a fancy word, but isoclines in general could apply to all points in the space of capital and consumption that have a slope equal to 2, or a rate of change equal to 2 per period. But here we're making it equal to 0 because that has a special interpretation for us, which is the steady state. Okay, so using the isocline concept means that we can take the first condition, the isocline for consumption, which says the rate of growth of consumption is a positive function of the difference between the marginal product of capital and the threesome population growth, depreciation, and the private discount rate, or the social discount rate, or the Ramsey's planner discount rate. And when that thing is equal to 0, then we must have a situation where KT is simply the level of capital per capita that has a marginal product that equals n plus delta plus theta. So that means that the isocline, or the C dot equals 0 for this model has to be a vertical locus. It's going to be a vertical line, and any point to the left of the vertical line implies C dot positive, and any point to the right of this isocline will imply C dot negative, declining. Okay, so the 4 arrows are drawn there just to give you a visual impression, but any point will have an arrow associated with the intensity of rate of change of consumption per capita that's associated with that equation. So the farther you get away from that line, the stronger that rate of change of consumption will be. Okay, now what about K? K also obeys a differential equation, which we described before, and this differential equation is familiar to all of you from the Solo model, but also from last week's discussion. And since we've shut down technical progress to make this easier, we can basically write that in the following way for all t. So the economy's resource constraint implies that any time that you're off this curve, you're going to have an implied change of capital towards the locus, and if you're below this locus, you'll basically have a rate of change of capital in the negative direction. So this is a similar type of isocline, except it's not a straight line or even a sloped line. It's going to be basically the same curve that we observed in the OLG model, and for the problem that Phelps solved, it'll look like the following. And therefore, if we're above the K dot equals 0 line, capital will be declining. And if we're below this isocline for capital, the capital stock will be rising. So what does this imply? This implies both of our equations of motion have to be sort of operative at any point in time. So every point in that CK diagram in the positive orthant has to be associated with 2 arrows, and the sum of those 2 arrows, the sum of those 2 vectors will give rise to motion in the next instant of time. So if we interact those 2 together, we can implement the so-called phase diagram. Okay, so I've done that, and you can see that these 2 curves imply 4 regions of the CK or KC space that involve different qualitative changes per unit time of the two variables of interest. So call K the state variable, the true state variable, and call C the co-state variable or the control variable. And you can see that if you're in the northwest or the southeast, all points in that space are going to be unstable. So they're all going to move away from the green dot, which is the intersection of the two isoclines. So basically, the only chance we have in this model of isolating any path that leads to the green dot, to the intersection, to the steady state, has to be starting in the southwest or the northeast part of the diagram, and they have to really be, if you like, on the right track. It's possible to show mathematically there's only one right track, there's only one path, and that's why it's called a saddle stable path, because any path off that path is sort of condemned to not attaining the green dot in finite time. Okay, so think of these arrows as describing the equations of motion or the laws of motion for this economy, and the way the model is set up, there's going to be exactly one path that makes it, and this can be solved for locally. You can use analytic methods to get the rate of change of both of those consistent with attaining the steady state summarized by the green dot, and they have to do with the eigenvalues of the dynamic system, but we won't discuss that in this class. Okay, so what good does this setup do for us? Well, it gives us the opportunity to change parameters that we considered fixed in the previous analysis and compare them with other values of the parameter and see how different the economy behaves, or how different the social planner would optimally choose the path of consumption and capital. So you might think this is a bit odd, because if the Ramsey planner is confronted with a population growth rate or depreciation rate or rate of impatience or some other parameterization of the model, then it's why would these things change? Either they're that way forever or they're not. Well, it's a bit of a philosophical question. This is often called an MIT shock, because in some sense these are not really shocks, but you're changing the parameter and starting afresh and maybe comparing two different worlds. It's still interesting, even though it may seem a bit strange, especially when we do the decentralized economy. Okay, so think of it, one convenient way, which is uncontroversial, is to think about studying a parallel world in which the agents of that world, the parallel world, have different utility functions or different depreciation rates or different population rates, growth rates. So there are two parts of this analysis. One would be just asking where does the new steady state land in this setup? Okay, so when you change one of these parameters, you'll change the static part, which is the steady state, and then there's this dynamics. How do we get there? And to do that properly, you really have to recognize that the saddle stability property for small changes will govern the system after the changes occurred. After you make the comparison, starting at some initial condition, you'll be off the steady state. So how do you get to the new steady state? And we can vary lots of parameters. I'll just vary a few in this lecture. We can discuss the subjective rate of time preference, call it patience if you like. And it's actually technically the higher theta is, the more impatient we are, the more we discount the future. Depreciation, the rate of deterioration of the capital stock if nothing is done, or the rate of population growth. We could even also change the level of technical sophistication, not in terms of the growth rate. To make this easier, we'll just shift the production function by a Hicks neutral multiplicative term. So here's a first comparative dynamics experiment we could do, which is just a decrease in the rate of time preference or an increase in patience for Ramsey, the central planner. So the central planner starts in this steady state, and suddenly the central planner becomes more patient. Then the new curve corresponding to the effect on impact, the C.0 isocline moves to the right, and moves to the right, implying a new intersection given by the new green dot in the upper to the northeast of where they started. But to approach that new steady state, the new central planner's plan must approach it from the southwest as before. And to do that, she will have to attain this dotted line that is the saddle stable path corresponding to the new steady state. So to get there, there will have to be a one-off change in the only jumping variable in this model, which is for the planner, which is consumption. And consumption can change at every point in time. And if consumption goes down, that means that savings or investment goes up. The capital stock, however, stays at the initial condition. So think of this as K0. Under the new conditions, consumption would have to be scaled back by probably not an insignificant amount. On the new regime, given this foregone consumption, more capital will be accumulating, which will lead to an expansion of the capital stock per capita, meaning the economy moves along the stable path with rising consumption per capita and rising capital stock per capita as the economy moves to the new steady state. So capital stock becomes larger per capita, which means that the capital intensity of the economy grows, and this is all a product, an artifact of an increase in the patience or a decrease in the rate of time discount of the social planner. The second experiment is an increase in the depreciation rate, which implies a downward shift in the capital isocline and a leftward shift of the consumption isocline. So the impact effect of this change is an immediate decline in consumption and then a steady decumulation of capital and a steady decrease in consumption along the path to the new steady state, which is marked in this slide. Okay, so the logic there would be that agents in this economy have to roll up their sleeves and basically deal with the fact that a capital stock costs more in terms of depreciation every instant, and that's going to sustain a lot less consumption than before. So that means that consumption will drop immediately to reflect that new pain, but also it will decline over time as the capital stock also is effectively consumed by the inhabitants of this economy because they can't sustain the higher steady state. So the new steady state is obviously at a lower level with a lower capital stock per capita. Last interesting experiment very quickly would be what would happen if we suddenly allowed capital to change its productivity in a multiplicative way. So if we move to basically multiplying f by a constant forever, which is greater than 1. Okay, and this would basically, logically, it's going to lead to more resources for all generations. It's also going to lead to a larger marginal product of capital for all generations at any given capital stock per capita. Therefore, it's in the interest of the social planner to accumulate. So that basically, we would see accumulation as we move from the old capital stock to the new K star prime. But because the production function is permanently more productive, consumption today can even jump today in a positive direction because the central planner knows that over the next million years, there'll be more resources for everyone to eat. So it makes sense for the agents to sort of grow into this. the current generation should also benefit, and that would cause the current generation's consumption instantaneously, according to this optimal plan, would see that this consumption per capita actually rises, and then upon impact, both capital and consumption per capita rise to the new green dot, to the new steady state. Okay, so now as I move to the next and last part of this lecture, I'm going to talk about the discussion of what it means to do the right thing. Ramsey is basically, as a social planner, is choosing the optimum optimorum, but the social planner has the freedom to do this. The social planner can choose any plan. Since the social planner doesn't exist, this is really just a fictitious object that we're using as a benchmark to compare the activities of a decentralized economy and whether a decentralized economy under idealized conditions could ever attain this social optimum. And of course, if firms have market power in their product markets or in the input markets, this may cause problems, and also if there are externalities like climate change, or for which there is no market, this equivalence could fail, but it's still worth talking about. So under which conditions could the competitive equilibrium actually attain the Ramsey optimum? Well, this is where we start to introduce prices and think about a household as we did in the OLG model with capital. The difference will be that there's completely interconnected internalization of future generations' utility. So think of the household head as being in charge of a population of the household that's growing. But the household cares about future individuals in this household in the same way that household head cares about her own utility. Okay, so we have this purely altruistic behavior, and we'll see how far this can get us. This is also in the book that you have been using in this class. Under these conditions, and if the social planner's impatience equals the impatience of the household head, the competitive equilibrium actually can exactly replicate the social planner's optimum. So we can use the same notation that we had before, and we can consider the problem of a household facing a path of wages and interest rates, choosing a function, and by way of the intertemporal budget constraint, we didn't directly choose the path of capital in that household per capita to maximize the utility of that household. Think of it as dynastic utility. So it would use the same discount rate, theta, and now we'll consider this policy as basically maximizing the same utility over this function ct from t equals 0 to infinity. But now that the household is using the market to acquire the resources needed to build up capital. So the household works LT, and we'll set LT equals to 1 later, but right now we'll just say in general, if the household could actually choose labor, and labor doesn't cost anything in terms of disutility, the household would supply all the labor that it has at her command. And then the household can rent capital, KT, in a competitive market and get RT for it. And then CT would be the consumption of that agent's household. And if you divide that by LT to make it a per capita, put it in per capita terms, we get a very similar equation to what we had before. Okay, so we have this wage per capita, and again, as you can see, I've implicitly assumed that the economy is fully employed, so the LT is equal to NT. It's growing at rate little n, and in per capita terms, it's basically the resources available to the household per capita as a function of the wage, positive function. It's also a positive function of the rental rate of capital with an adjustment for the fact that there are more and more people coming online every period, and of consumption per capita. And there's an initial condition. So you can write down the optimality conditions using the the Pontryagin maximum principle applied to the household now, and have the same sort of type of first order conditions that we described before. And it turns out that under these conditions, we have a very similar outcome to what we had before. So we have if you let RT be if we define RT as the marginal product of capital net of depreciation, then we effectively have derived the same types of first order conditions that we had before, except they're now involving market prices and rather than planned quantities that the central planner would have chosen. Okay, so we still have an elasticity of substitution governing the behavior of the profile of consumption over time, the rate of change of consumption over time relative to population growth and impatience, and we have the capital stock evolving with respect to its remuneration plus the other income that the household might have, and since the household is supplying 1 unit of labor every period per person, then this is just the wage. So we can have a private Keynes-Ramsey rule which governs the rate of change of consumption as a function of the elasticity of substitution multiplied by the rate of return on capital after depreciation is subtracted relative to the rate of growth of the individuals in the population in the household, plus the impatience of the planner. So we have the same type of analysis with the elasticity of intertemporal substitution, except now it's actually applied to a small change in the rate of return on capital. So it kind of confirms the intuition that along the optimal path, if consumption per capita is rising, that must mean that the households have deferred a lot of consumption and are going to reap the gains of that deferred consumption in the future as capital accumulates and more output is produced. Now, there are firms in this decentralized economy that we haven't talked about in detail, but in fact, these firms basically take prices of the factors of production as given. So they hire labor and capital at rates omega and R, and this is exactly what the factor price frontier was before in the OLG analysis. So in a sense, because we have a constant returns production function, capital and labor absorb all the output after depreciation is subtracted. So basically, national income is partitioned in the neoclassical fashion that we discussed already in class. Okay, so the market equilibrium, when supply of labor and capital equal demand and the goods market clears, will basically look very similar to what we had before. Again, we have to impose that households don't irrationally accumulate capital without end, although they could have actually consumed it, i.e. not continued to maintain it. So we have the same type of condition that we had before. And if we do that, if we impose that, we're going to get precisely the conditions that Ramsey's analysis isolated at the beginning of the lecture today and the lecture last time. Okay, so just substituting for these objects gives us back what we had before. So this means under these very, very idealized conditions, the centralized planning solution can be replicated by the market if the conditions are right. Okay, so in the steady state of this general equilibrium, the rate of return on capital is the marginal product adjusted by depreciation, and that's going to be equal to the rate of impatience plus the rate of population growth, and the wage will be the marginal product of capital after, the product of capital, the output of capital implied by capital per capita after capital is paid, its marginal product. So constant returns in production ensures that the net product per capita is actually paid out, and there are no excess profits beyond the marginal product. And that's just an artifact of neoclassical production. We don't have any market imperfections. All these things should be clear to you. Under these very restrictive conditions, the market outcome is Pareto optimal. Now, these two gentlemen actually gave us that result in the 1950s. They said that it is possible that a market outcome can be Pareto optimal, and it can also be possible that a social planner's solution can be replicated by an appropriate choice of initial allocations of wealth at the beginning of the trading in this economy. So the first and second welfare theorems proved by Kenneth Arrow and Gérard de Breu are known as the first and second welfare theorems. Kind of what Adam Smith said, basically turning it on its head, if you like. A market outcome can only be improved on by taking something from someone else. The decentralized market equilibrium is Pareto optimal, and if you have a planner solution that you've identified and you have these conditions that are met, you can also reverse this. So the first welfare theorem requires a lot of assumptions. And you can see that constant returns to scale is just one of them. Perfect competition, absence of externalities, no climate change, complete information. So kind of unrealistic, but nice to know. It's a benchmark. The second welfare theorem talks about the reverse engineering. Is it possible to achieve a social planner's optimum as a decentralized market outcome if we choose the endowments properly? And the answer is yes, but we have the same four conditions we needed before. In addition, we have a technical assumption about the preferences of the agents and the convexity of the consumption set. So these are really strict conditions. It's unlikely this will be holding in reality, but it's still good to know that the market outcome can be attained under certain conditions, and just to be honest and recognize that they're like this. So let's finish up the lecture talking about policy implications. So one is that if the market is producing some outcome that looks a little bit like our Ramsey outcome, we should actually be aware of the fact that it has an implication for the level of interest rates, which might be relevant today. We know that real interest rates are low. We also know that nominal interest rates are low, but we also know that real interest rates are really low because we have positive inflation at the moment, and we've had positive inflation even while having zero nominal interest rates. So that means that, is there any way that these theories can explain this? And the answer is yes. Okay, you can imagine in a case where, at least the model can explain very low or even negative real interest rates under certain conditions on these parameters that are in yellow. Okay, so if technical progress were to turn negative for some extended period of time, that would be an easy one to grab, but it's very unlikely. Impatience, growing patience of the economy would mean a theta that's decreasing, and maybe even a theta that's decreasing a lot, and population growth could also theoretically go negative. These are possible ways to explain how the real interest rate might be very low or even negative. To be honest, we haven't spent a lot of time talking about technical progress, but it would definitely add another layer of explanation. But certainly the changes in the real interest rates that we have observed over the past, say, 10 to 20 years could be associated with decreases in the rate of technical change, in a decrease in impatience or an increase in impatience, or a decrease in the population growth. This is often called secular stagflation. It's associated with Professor Summers from Harvard. And it's an alternative to just blaming monetary policy. We'll talk about monetary policy in the second half of the course. This would be an alternative, and the reality is probably somewhere in between both. Second set of policy implications flows from Ricardian equivalence. We've already discussed this. The agents, individual agents are obeying an intertemporal budget constraint, and taxation is non-distortionary, then you can see that the intertemporal budget constraint is going to be independent of the path of taxes, because if the agent has to pay high taxes today and the government obeys its intertemporal budget constraint, then the taxes will have to be low in some point in the future. And if government and agent and the household are borrowing and lending at the same rate, then this should be a wash. There should be no net effect on the resources available to the private agent. And under these conditions, the value of government debt should be rather low, because the agents know that this debt is held by somebody who will eventually have to pay the taxes on that debt, on the taxes on income that is needed to finance, to service or even repay that debt in the future. Okay, so if you think about it, the household's budget constraint would be shifted by the government's claim on resources from the spending side, but eventually all this has to be financed by taxation. So a tax cut per se that's financed by an increase in taxes in the future should not have any effects. Okay, so I'm done. Key concepts to remember. Our friend the Lagrange multiplier. You can think of this as also as the implied co-state variable in the analysis. We'll end up relating that directly to the control variable, but the current value versus present value is an important distinction, especially when you're trying to solve one of these problems. The elasticity of intertemporal substitution, how does the profile of consumption respond to a change in the intertemporal incentives to save over time, holding actually total wealth constant. Comparative dynamics, how can we use these tools to think about different economies under different conditions, and if you're brave, you can even think about a change in these conditions, but again, that's kind of stretching the interpretation. We talked about normative versus positive economics. I remind you that normative economics is what we think the economy should be doing, so it's a policy recommendation, or if we want to optimize the utility of all the generations that are alive, it's the Ramsey problem, if you like, whereas positive economics involves just studying how the economy behaves in a market or under certain conditions that may not even be perfect. And the great economist Lionel Robbins made a very, very clear statement of his view of positive economics, and he said that we should be doing mostly positive economics and letting the politicians do the normative stuff. So we advise the politicians on what happens if you do A or B, but we're not going to tell them you should do A or B because the politicians are elected to do that and we're not. So it's a fairly nice way of looking at it. I think Lionel Robbins said that a botanist should not be in the business of telling people how to plant their gardens. He should tell them what they should do if they want to have a garden that looks like this or a garden that looks like this. Okay? That gives rise to the idea of a decentralized economy where agents trade with each other and are not being directed by a central planner. And that gives rise to this notion of a representative firm. One does not have to have representative firms in households in a decentralized economy. Indeed, one of the most exciting areas of economics now in macro is to look at how many different types of representative agents weighted by their populations interact with each other, so-called heterogeneous agent model. And then we have this notion of Pareto optimality, which means that have we reached a situation where a reallocation of ownership of resources makes one agent better off only at the expense of the other. That would be a Pareto allocation would be one where it's not possible to increase the welfare of any agent without decreasing the welfare of some other agent. Okay, this is not to say that you don't want to do this. I mean, raising taxes on rich people and giving the money to the poor people is kind of a solution to some general problem, but if we can't achieve a better allocation without doing that, then we indeed have some sort of Pareto optimality involved. Okay, and then First and second welfare theorems we talked about already, and we talked about Barrow regarding equivalence again, even though I mentioned it earlier in the context of the OLG model, because it does have a parallel discussion. Increasing debt in an OLG model is more likely to have real effects than introducing government debt in a infinitely lived model of identical households. Good. That was the lecture for today. Thank you very much for coming, and I hope to see you next time.